Hello students, let's begin with a little riddle. How can two atoms of the same element behave exactly alike in a chemical reaction, yet differ in mass? The answer lies in the fascinating world of isotopes. Isotopes are atoms of the same element that have the same atomic number, meaning the same number of protons, but different mass numbers due to differences in the number of neutrons in their nuclei. So, here's the definition. Isotopes of an element have identical chemical properties because they contain the same number of protons and electrons, but they differ in their physical properties because of their different atomic masses. This is why, when you look at the periodic table, atomic masses are often fractional. Isotopes make the average atomic mass not always a whole number. For example, hydrogen exists as three isotopes: protium, deuterium, and tritium. All three have one proton, but protium has zero neutrons, deuterium has one, and tritium has two. But how do scientists keep track of all these different forms? Isotopes are represented by writing the element symbol with the mass number as a superscript and the atomic number as a subscript. For example, protium is written as H with 1 as a superscript, so 1. H deuterium is written as H with 2 as a superscript, 2. H tritium is written as H with 3 as a superscript, 3H. Let's a formula is the neutron number equals mass number minus atomic number. So for deuterium, that's 2 minus 1 equals 1 neutron. This notation makes it easy to see an atom's internal structure at a glance and helps distinguish between isotopes of the same element in chemical equations. Scientists also use special names like carbon-12 and carbon-13 to keep communication clear and precise. Now, here's something truly interesting. Isotopes of the same element have identical chemical properties. Why? Because chemical reactions depend on electrons, and isotopes of an element have the same number and arrangement of electrons. But physical properties like density, melting point, or rate of diffusion can differ among isotopes because of the different atomic masses. Let's take heavy water, which is deuterium oxide D2O. It's physically distinct from regular water, H2O, but chemically, both act as water in reactions. By understanding these differences, scientists can separate and use isotopes for specialized industrial and research applications. Most elements you encounter aren't made of just one kind of atom, they're mixtures of isotopes. Each isotope is present in a certain percentage, known as its relative abundance. This is why, for example, the atomic mass of chlorine is about 35.5 instead of a whole number. It's because chlorine is found as a mixture of two main isotopes, chlorine 35 and chlorine 37. The relative abundance of each isotope is what determines the average atomic mass seen on the periodic table. Let's write a formula. Average atomic mass equals the sum of open bracket isotopic mass times relative abundance close bracket for all isotopes divided by 100. Let's solve a real calculation. Suppose 75% of chlorine is chlorine 35 and 25% is chlorine 37. Average atomic mass equals open bracket 35 into 75 plus 37 into 25 close bracket divided by 100. Let's go step by step. 35 into 75 equals 2625. 37 into 25 equals 925. Add them together. 2625 plus 925 equals 3550. Now divide by 100. 3550 divided by 100 equals 35.5. So, that's how we get the average atomic mass for chlorine as 35.5. Isotopes aren't just a scientific curiosity, they're essential tools in our lives and technology. In medicine, Radioactive isotopes called radioisotopes are used for diagnosing and treating diseases. For example, cobalt 60 is used in cancer therapy, while iodine 131 is used to treat thyroid disorders. In industry, isotopes help in tracing leaks, measuring thickness, and even in research like carbon 14 dating to find the age of ancient artifacts. Deuterium is used in nuclear reactors, and heavy water keeps our power plants running safely and efficiently. So, from archaeology to atomic energy, isotopes have real world value. Let's quickly sum up what we've discovered about isotopes. Isotopes are atoms of the same element with the same atomic number but different mass numbers, which means they have the same chemical properties but their physical properties can differ. Isotopes explain why atomic masses aren't always whole numbers and why elements can be used in so many amazing ways, from medicine to industry to archaeology. Remember, the notation, element symbol with mass number as superscript, helps chemists everywhere communicate clearly and identify isotopes instantly. I hope this session has helped you see how chemistry goes beyond equations and symbols. It helps us understand the invisible world inside every drop of water, every fossil, and every nuclear reactor. Catch you in the next class where we'll explore more wonders of atoms and molecules.